Hello and welcome to section 10.4, Scalar Products and Projections of Vectors. At the end of this section, we should be able to answer these questions. What is the symbol for a dot product? What are the two ways to calculate dot products? What are the two other names for the dot product? What is the meaning of the vector projection of one vector upon another? What is the meaning of the scalar projection of one vector upon another? How do we calculate the scalar projection quantity? How do we calculate the vector projection quantity? What are the formulas for the scalar and vector projections that don't include the angle between the vectors? Well, let's start with some definitions. The dot product is also known as the scalar product and the inner product. All three of those names refer to the same idea, where theta is the angle between two vectors when they are translated tail to tail, and we use these symbols to denote the dot product. We use the little dot, obviously. So this would be read A dot B for the dot product of the two vectors, and it's calculated by calculating the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. Now, if we think about what that formula might imply, we can look at the different quadrants that the cosine of theta could be in. Now, the angle between the two vectors has to be between 0 and 180 degrees. Once it becomes more than 180 degrees, we use the other side of the connection between the two angles to measure. So we keep the maximum angle between the two vectors to 180 degrees. If theta equals 0, then our formula simplifies because the cosine of theta of 0 degrees is equal to 1. So the dot product at that point, A dot B, is simply equal to the product of the magnitudes. Now, if theta is between 0 and 90 degrees, that puts us in the first quadrant, and we recognize that the cosine of theta in the first quadrant is positive. So cosine theta is greater than 0, which means that my dot product would also be greater than 0. Now at 90 degrees, the cosine of theta is equal to 0. Which means that when my two vectors, when connected tail to tail, form a right angle, my dot product will be equal to 0. So if my vectors are perpendicular, their dot product is 0. When theta is in the second quadrant, between 90 and 180 degrees, so my vectors form an obtuse angle, we know that the cosine in the second quadrant is negative. So cosine theta is less than 0. Which means that my dot product will also be less than 0 because magnitudes are always positive. So without a lot of calculation, we can determine whether or not the angle between my two vectors is acute or obtuse. Now, if theta is equal to 180 degrees, we know that the cosine of theta is negative 1. So at that point, my dot product will simply be the negative of the product of the magnitudes. Alright, so if we have information about the magnitudes and the angle between them, we can calculate the dot product. There is another way to compute the dot product if, instead of their magnitudes and direction, we have the components. And here, while the wording sounds somewhat intimidating, the dot product of two three-dimensional vectors equals the sum of the respective products of the coefficients for the I, j, and k unit vectors. It's really a very simple calculation. If I have the three components for each vector, I simply multiply the x's, and multiply the y's, and multiply the z's, and then add them together to get the dot product. Straightforward. So here's an example. I have two vectors, c being 4i minus 6j plus 9k, and d being 2i plus 5j minus 3k. To calculate the dot product, I simply multiply my x's, so 4 times 2, then add the product of the y's, so negative 6 times 5, and add the product of the z's, so 9 times negative 3. So that gives me 8 minus 30 minus 27. So minus 22 minus 27 should be minus 49. Now to find theta, we need to combine the two ways of calculating our dot product. We remember that the absolute value, or magnitude of A, times the magnitude of B, times the cosine of the angle between them, should be equal to our alternative way of calculating the dot product, which would be the negative 49 that we calculated in the previous example. So the magnitude of A, we need to use our super Pythagorean. So the magnitude of A is going to be equal to the square root of the sum of the squares of the components, or C in this case. So 4 squared plus negative 6 squared plus 9 squared, which is going to be the square root of 16 plus 36 plus 81. So that's 52 plus 81. So 133 square rooted. For the magnitude of D, our second vector, here we have the square root of 2 squared plus 5 squared plus negative 3 squared. And that's going to be the square root of 4 plus 25 plus 9, which is the square root of 38. So now we know that the square root of 133 times the square root of 38 times the cosine of the angle should equal negative 49. Now just by looking here, since it's equal to a negative dot product, or a negative value, we know that the angle between the two vectors is obtuse. So cosine theta is equal to negative 49 over the square root of 133 times the square root of 38. And to find theta itself, we just need to take the inverse cosine. So theta is going to be equal to the inverse cosine of negative 49 over the square root of 133 times 138, square root of 38. So pull out our trusty calculator. First, let's move this over so we can see it. Pull out our calculators, and we will take negative 49 and divide by the square root of 133, and then we will divide again by the square root of 38, and then we will take the inverse cosine of our answer and come up with 133.571 degrees. Which confirms our initial estimate that theta was going to be obtuse.